Hello. Now I'm going to manipulate the model that I created in the video one to show you some hydraulic phenomena. Basically, in this very simple model, I have a river with just two cross sections at the very upstream and very downstream locations. So you can take a look. This is my upstream one. The bottom elevation, invert elevation is 9 feet. Now in the other one, it's 7. So 2 feet drop over around 100 feet of horizontal distance. You can see downstream leach length is 100. And I have a rectangular shape with some very simple figures for the overbank. So now I want to do some manipulations. So through that, you can see some options you have in HEC-RAS. So basically your geometry, of course, in the cross-section toolbar, you have different options. You can adjust elevation, you can station, multiply by a factor, add a constant, adjust n values, create obstructions, different things. But you can even add a lid, ice cover and everything. But what I want to do right now, under the main geometric data, you also have some options and tools. Like this one, a very useful tool is you want to interpolate within a reach or between two cross sections. So basically, if I want to do anything to this, like right now you can see my profile. For example, if I want to create a transition, a step in this for, let's say, 1 foot rise step, what I need to do, I need to have some cross sections so I can manipulate it. Right now I don't have it. So first step for me is to create some midpoint cross sections so I can manipulate it. The easiest way for that is through these tools, interpolations between the two cross sections. I have 101. So let's say at each 200, at each 20 feet distance, I want to interpolate something. So then the interpolation is created for me. I close it. Now you can see I have nicely created 5 cross sections in between. So if I save this, I can go to my profile. Now you can see I have one at 80, one at 60, 40. So then now I can easily create a step rise here between station 60 and 40. So let me do that. So at 60, I want to edit this. And basically what I want to do here, I can either just basically shift this for 1 foot up. So at this, instead of 8.2, I can do it 9.2 and 9.2 here. So basically showing what happens if I have a rise in the channel bottom as a transition. So you can see this is rising. Now I want to go further down, do the same for 40. For 40, I want to do step. So this is 8 and 1 foot rise. This is also 8. So apply data. Then this gives me some idea. If I take a look at the profile view, now you can see I have this rise. So as you can see, the results are not up to date. I'm going to rerun this to see and observe what type of results I get with this transition that I created in the channel. So let me do that. And that's under the flow. So I'm just running for 10 CFS, and let's do this one by one so we don't confuse. So 10 CFS, it's good, save it. And geometry is okay. Now I go to my run window and run it. Make sure I have the meaningful boundary condition to run it. So yes, in this case, I have the very, very flat situation. So let's bring it back to something that can, produce basically type of uniform result that I first tested in the first video. So 1% for normal depth, okay it, and then save it and run it. So basically the model is solving with the more cross sections I have, and then I can generate the cross sections. So you can see how this changed. Without this transition in the beginning, I had a very uniform flow. When I ran it in the first video for 10 CFS, it was uniform and critical. But now this transition, it's causing some choking situation, as you can see. This is what we refer to choking through the lectures. The water before the transition doesn't have enough energy to make it to the transition. So choking happens, the water slows down, and then with the slowdown, it creates a higher depth. And that higher depth is now enough to pass through this. So as you can see, this is a very interesting phenomenon, so I maximize it. The red is my critical depth, right? The red dash. So you can see basically because of the choking condition, the water is passing through the transition at its critical depth. So the red dash is exactly same location as the water depth. So that means that basically water is at its critical depth when it goes to this transition. That's because of the choking condition that we explained in the lecture. So these are different things you can easily test in HEC-RAS. You can change the condition if you want to see what happens for a flow that is already supercritical. Then we can also test that. So let me test that. Let me in this case, we started with a subcritical flow and understanding its behavior over a transition. Let me now change this. So if I want to change this, then of course I need to create a supercritical condition from the boundary condition. And I want to run this supercritical. So let me save this. And here in the boundary condition part upstream, that's something I need to have. If I don't add this and I run the model, it shows me an error. You're missing a boundary condition for upstream, because when you run it supercritical, you need to know your boundary condition from the upstream side. So I'm going to add that upstream, let's say critical depth, and I okay it and I save it. So now I can run it in supercritical mode. So now I am passing a supercritical flow through the transition. Let's compute and see what type of results we will get. So go back to our profile. Now you can see it's different. No choking. You start with supercritical, and then you start actually with critical depth, and your flow is supercritical. So you don't get to the choking figure. You see the flow is passing supercritical across the system. Your depth at all location is below the critical depth. That means it's flowing very fast. It's all supercritical. So how boundary condition change this? We have still 10 CFS. The only thing that changed here is our flow regime. First part, I ran it subcritical, and then the boundary condition for that was a downstream slope. So choking happened and it became critical for the entire system. Now I'm changing it to supercritical, and supercritical stays the same regime, as you can see, throughout the system. So just showing you an example of how to manipulate your cross-section with interpolation, how to run your model in subcritical or supercritical situations.